Okay, hey everybody. Welcome back to 341. I'm not sure. Let's check and see. Okay, there we go. For some reason, YouTube sometimes doesn't show me the chat. Not that anyone said anything. Okay. So, alright, so where were we last time and where are we going to be today? So I imagine today is going to be mostly a project day. So, if you have any trouble with the project, I'll be around after class. If you're finishing up, running tests, that kind of thing. What's the other thing to say? I think I've just decided that we're going to just release... I have a homework assignment that I pre-wrote. Ignore the fact that it says homework 2. This was from a previous semester. I think I'm just going to release this one. It's a decent homework assignment. Hopefully everybody will love it. And then I'll release that today. I'll just put it up on the actually, yeah, let's compile it. And okay. Nope, not Python. Okay, once this is compiled, the other thing to say is that I think what I'm going to do is we also have an exam coming up. I guess maybe I'll release it. Maybe I'll release it next Tuesday. Before I release the exam, I wrote up this practice thing for last semester. It's this huge, big blob of document. It has a ton of different questions on it. Some of it we haven't gotten to yet. So I would say, basically, if I'm going to release this, maybe I'll take out some of the stuff, because this is more than exam 2. This is really like the final exam practice. And then here is an exam 2 that I gave. So what I'm probably going to do is maybe Thursday I'll go over this, and or at some point maybe I'll go over this, at least some of it. It looks like here I won't go over anything past here because this is stuff we haven't covered yet. Yep. Okay. So basically, that's my plan. So we'll release the homework sometime today, and I guess I could actually just release it now on Discord. That would not be impossible, so let's just throw it up. Okay. Alright, there it is. I'll release it more formally after class. Okay, so now getting back to binomial heaps. So basically, I wanted to talk about binomial heaps again, because we haven't really fully gone through them. I mean, we've done a little bit, but we haven't really done enough to really cover them. So if you remember, right, let's actually move this up so that it looks uniform with all the other ones. So remember how we define these b sub i's, right? The rule is to construct a b0 is simply a node, right? So a b0 is always just a single node, right? And then the rest of them obey the rule. So the rule is that you take 2 of the previous ones and you kind of merge them together, but you merge them together in this way, where you take one of them and you make it the leftmost child of the other one. So notice here, here, this could be a binary tree or a linked list. Here, this could be a binary tree. Here, this is definitely not a binary tree. So that's something I didn't actually mention last time, which maybe you noticed, maybe you didn't, this is definitely not a binary tree. And so what do I mean by that is that each node can have, actually it's not even necessarily a ternary tree, it can have as many children as it needs, right? Because here you see that a B4, the parent in a B4 has 4 children, the parent in the B5 is going to have 5 children. So the parent in the like topmost parent in the Bn is always going to have n children, right? Here's this B5 thingy that has 5 children. So there's some cool mathematical facts about, there's 2 cool mathematical facts about binomial heaps. And then there's the, and then there's implementation. So, what do you want to do first? We have 3 things to do today. One is visualization, using that website, which I think is pretty good. The next thing is maybe math proofs. And the third thing is live coding of a binomial heap. And I'm not sure if I've ever actually done this, so this is an experimental thing. I might or may not be able to actually finish live coding it in a single lecture. So who wants to do, so let's all do 1. The question is, who wants to do 2 and who wants to do 3? Who likes math proofs and who wants to do live coding? And while you're thinking about that, I'll pull up my binomial heap visualization. Okay, they're calling it a binomial Q. Vote now, right? So, okay. So let's look at the binomial Q, and let's see what we've got going on here. So let's say let's insert a few things. Let's insert 5. I always insert 5 first. I don't know why. Now let's insert 2. And then what happens when we insert 2? What's going to happen is, very quickly, and because I have the speed set to insano speed, it's going to go too fast. And let's insert 15. Okay. Insert, say, 31. So remember what happens when we insert a node. So the point here is there's 2 B0s, and that's the only rule, is that you cannot have 2 of the same BI in your final structure. When you're merging, you can have as many as you want. Technically, you'll only have 3, but I'm just saying as many as you want because there's no specific rule. But once you're done merging, you only can have 1 of each. So what you're going to have to do is merge these 2. So in order to merge them, it's going to make 31 the child of 15. The reason is because 31 is bigger than 15. This is a min heap, by the way. You see, 2 is the parent of 5, 15 is the parent of 31. And then we see here, we have to merge these 2 because now there's a B1 conflict, and that's how it's resolved. 2 is less than 15, so 15 goes down and becomes the child. All right, let's insert 35. Skip. Insert 42. 42. Insert. So here we go. It's trying to merge. It sees that there's 2 B0s. It merges them into a B1. Does it need to merge the B1s into a B2? It doesn't. Right? Stop. Insert 25. Let's go. There's a B0, there's a B1, there's a B2. So remember the binomial, or not binomial, remember the binary representation of this. The binary representation of this, unfortunately, is basically 1, 1, 1, right? It's basically 1, 1, 1. So what's the problem with that? You know, and the answer is if we insert another 1 in here, right, and we add them together, let's say we put a plus sign. Of course, it's a font that's not uniform in width, so unfortunately I'll never get it completely under there. So remember, if we're going to add these together, 1 plus 1 is 0, carry a 1. 1 plus 1 is 0, carry a 1. 1 plus 1 is 0, carry a 1. So in the end, what we're gonna, well, let's actually just like space this one more so that it's more aligned. And so the point here is that if we look at this, what we have is, unfortunately, once we have a full one and we add another node, this means that we have to carry 3 times, right? Because what's going to happen is 1 plus 1 is 0, carry a 1. 1 plus that carried 1 is 0, carry a 1. 1 plus 1 is 0, carry a 1. So this was 7 plus 1 is 8, right? 7 plus 1 is 8. So let's watch binary addition happen. So let's pick a number, say 22, and let's insert it. So when we insert it, we see that there's 2 B0s, so we have to resolve that. Now there's 2 B1s, so we have to resolve that. And now there's 2 B2s, so we have to resolve that, right? And so we see here that that's how this process works, right? And now we have a B3. And you notice that a B3 has 1, 2, 3, 4, 5, 6, 7, 8 nodes. So as it turns out, the BNs always have 2 to the n nodes. That's a thing that we can prove. That's one of the 2 mathematical identities that we can prove. Yeah, so let's insert 17. Let's skip forward. Let's insert 46. I don't know, I just picked something at random. Insert, skip forward, and then maybe 33, right? Insert, and skip, right? Because we basically know how this is going to happen. So we have a B0, we have a B1, and we have a B3. Now, how do we DQ the max or the min, right? So how do we get the max, I keep saying max, how do we get the minimum out of this thing? So remember what we do, we look through all the head nodes, the root nodes of all these little trees, and we pick the one that has the minimum, and then what we do is, so it's looking here, it's saying, okay, these I guess are not the minimum. I don't know why the reds are only here and not here. I guess what it's going to do, let's see if it deletes it on the next step. Okay, no, there it goes. And now, okay, 2 is the minimum. Cool. So now it's going to delete that one. And now look what it's going to do, right? It's going to run its merge algorithm, right? It's going to merge 7 with 3, right? So what is 7 plus 3? 7 plus 3 is equal to 10. I had trouble with that for a minute. I did. Oh my god, anyway. And remembering that 7 plus 3 is 10, we know that in binary that's 1, 0, 1, 0, so we're going to end up with a B3, a B1, and no B2, and no B0. So that's how it's going to end up. So let's watch that happen. So here we're going to have to merge together these 2 B0 nodes, right? Okay, that's fine. I don't care. And now, okay, so now it's going to merge these together. What do we see next? What we see next is that there's 3 of them, right? And why are there 3, right? There can only ever be 3, and the reason why there can only ever be 3 is what? It's because there's literally 2 of them that already existed from the previous process, and one of them that's the carry. So let's see how it deals with this. I think it's going to merge 15 and 17 together. I could be wrong. Yep. Again, it really doesn't matter which ones you pick to merge. You could have merged 5 with 17, 5 with 15. The only rule, and there's no particular rule here, the only rule that exists is that you have to get rid of 2 of the 3 of them. So generally your code is going to make some decision, like you'll always merge the carry with whatever one is like the first one, whatever that means. But again, it doesn't matter as long as 2 of them get merged and you end up with a B2 here, and then B2 and B2 have to merge and give us a B3. And that's how it works. That's it. Right? And we're done. So now we notice if we try to remove smallest, let's try again. So no one's voting. I like this. No one's voting for either math proofs or live coding. So it's going to be math proofs because I like math proofs. So you notice that it deleted 5 here, and it deleted 5, which was part of a B1. And you notice the cool thing about this is that when it merged it back in, there's no B0, so there's no need to do any other merging processes. There's nothing, you don't have to do anything here, right? It's just literally just merge it in and you're done. That's it. So that's all you really have to do here. Okay. So all right, and then say we remove the smallest again. Let's just see what happens. Same thing. It's going to merge the B0s, but then this is kind of a nasty condition because this is 7 plus 1 is equal to 8 again. So we have to merge the 2 B0s into a B1, have to merge the 2 B1s into a B2, have to merge the 2 B2s into a B3. So you had to merge all the way up. All kinds of carries going on. Okay. So, fair enough. Fair enough. All right. So I think that's enough for visualization. I think we've gone through it, and I mean, there's no difference if you end up with B4s, B5s, B6s all the way up. The only thing about the higher ones is just that there's tons more nodes, right? So, yeah. Okay. So let's I guess let's do the math proofs next. So there's two cool facts about binomial heaps. We can call them theorems if you want. And then maybe some time analysis. So, but we need these facts to do the time analysis, so let's just get those facts first. So the first fact is that at level k of a Bn, the number of nodes is n choose k. Right? Now, of course, what I mean by n choose k is, I'll just write it out. Let's write that out. So there's two ways to think about n choose k. Right? Some formula. Right? That's one way to think about it. There's a formula for it. Here's the other way to think about it. So the other way to think about it is, if you have a bag with n things in it, it's the number of ways to pick k objects out of it. So if we have a bag, for instance, that has, say, 1, 2, 3, 4, 5 in it, right? There's little maybe pool balls or billiard balls or whatever that has 1, 2, 3, 4, 5 in it. How many ways can we pick 3 of them? And so if we think about it, you can say, okay, I can pick 1, 2, 3. I can pick 1, 2, 4. I can pick 1, 2, 5. I can pick 1, 3, 4. I can pick 1, 3, 5. I can pick 1, 4, 5. All right, let's keep going. I can pick, now let's start with the 2s. I can pick 2, 3, 4, 2, 3, 5, 2, 4, 5. Did I miss something? Not sure. I think I didn't. And then for the 3s, I can pick 3, 4, 5. And you notice that I'm doing this in order. The order doesn't matter here. It doesn't matter whether I picked 3, 2, 1 or 1, 2, 3 or whatever. I'm just basically picking them all like this. Okay, so how many ways was this, right? And so the answer was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so now let's calculate. And of course, you might ask, well, how do I calculate? The answer is, let's pull up that formula. So the formula is that, well, let's see. think that's how I like to do it, just to ensure that there's no problems. Frac n factorial over k factorial, n minus k factorial. Okay, so here's the formula for it. And so now let's stick in the numbers. Let's stick in 5 and 3. And of course, I haven't really talked to you much about what factorial is, but hopefully you know what factorial is. Maybe I'll do a little review on that in just a few seconds. So here's the formula with this put in. And so remember what factorial is. So n factorial, right, is equal to n times n minus 1 times n minus 2, all the way down to, say, 3 times 2 times 1. And now, some people always ask whenever I do this, but what if it's 2 factorial? Then it doesn't include 3. Yes, I know. Right, so basically, and the other fact is that 0 factorial is equal to 1, right? So so this is 0 factorial is equal to 1 is not determined by the rule above. 1 factorial equals 1 is basically, you just have to ignore the fact that it goes up too high and just say, oh, 1 factorial is just n, right? N is equal to 1, so there's nothing in between. 2 factorial is equal to 2 times 1. 3 factorial is equal to 3 times 2 times 1. 4 factorial is equal to 4 times 3 times 2 times 1, etc. 5 factorial is equal to 5 times 4 factorial equals 5 times 4 times 3 times 2 times 1 equals 120 equals 24 equals 6 equals 2 equals 1. So now we can calculate the actual value here. So this is equal to, the top is equal to 120, and the denominator is equal to 6 times 2. So we get 10, right? And so that is how we pull out 10. And then you say, wait a second, 200 years ago, you said that that there were 10 of these combinations. And I say, yep, there's 10. And that's how you compute it with the formula, right? So those are the two ways to calculate this value, right? You can either calculate it by writing them all out, which is probably pretty nuts if you're going to have anything close to, if you're going to do 20, choose 5. I promise you're not going to want to write out the number of combinations. It's not going to be, it's going to take you a long time. A computer can do it. 20 choose 5, a computer can still do it, but like 1,000 choose 250 or something. It starts to get large. Anyway, okay, so so now that we have all this done, so the fact one is that at level k of a Bn, the number of nodes is n choose k. And I think I made them prove this on an exam once. But that did not go well. I don't think people liked that. So let's copy paste a whole bunch of BIs, and let me just show you what I mean by level k, right? So this is B0. So so this is really like 0 choose 0, right? And we'll call this, for no particular reason, we'll call this level 0, okay? So this is going to be level 0. This will be level 1. This will be level 2. This will be level 3. And then, of course, that is all the same for the B4, except now it has a level 5, or no, I'm sorry, it has a level 4 attached to it. Let's stick these at the appropriate levels. Yes, there we go. Okay, so basically we're going to do this by induction, right? Just like everything in data structures, the proof is always, well, I shouldn't say always, but the proof is almost always by induction, so the proof is by induction. And so what we're going to do here is we are going to look at a B0 and say it has only level 0, 0, only has one node, and only has, what should I say? Only has level 0, only has one node, and so 0 choose 0 is equal to 1. And so you might ask, well, why is 0 choose 0 equal to 1? Well, here's why. 0 factorial over 0 factorial, 0 factorial. Remember, the definition of 0 factorial is equal to 1. So since the definition of 0 factorial is equal to 1, notice that 0 choose 0 is equal to 1, right? So this is equal to 1, and that is the number of nodes at level 0. And so, you know, if we look at these other nodes, is 1 choose 0 and 1 choose 1 equal to 1? The answer is yes, because 1 factorial is 1 divided by 0 factorial 1 factorial, or 1 factorial 0 factorial. They're both 1. So that's also leading credence to here. And then B2, so let's calculate C42. This is another way of doing the 4 choose 2. So this is equal to 4 factorial over 2 factorial times 2 factorial, which is equal to 24, right? 4 times 3 times 2 times 1, divided by 2 times 2, which is 4. So we're going to get 6. Wait, what am I doing? C42. Okay, C42 is not this at all. This is C21. Okay, this is C42, right? Because this is level 2 of a B4. But whatever. So let's put this calculation over here, because that's what I'm actually doing. That was, I don't know why I jumped all the way to C42 rather than C21. Okay, but we notice that it says 6 at the end, and we count 1, 2, 3, 4, 5, 6. So there's 6 nodes at the second level of a B4, right? There are, and then, okay, now let's think about C21 is equal to 2 factorial over 1 factorial, 1 factorial, which is equal to 2. C20, which is the 0th level, is equal to 2 factorial over, I guess, 0 factorial, which is 1, times 2 factorial, which is 1. And then C22 is equal to 2 factorial over 2 factorial, 0 factorial. And I'm not putting in the parentheses properly, so just going to have to assume that the parentheses are the correct ones in order to make this work. So, okay. There we go. So we've done it explicitly. So at this point, all we've done is base case, right? We've done 1, 2, 3, 4, 5, 6, 7-ish base case calculations. So we can stop with the base case, right? Stop with the base case, right? Sometimes it's good to do more base case calculations, but this is really all you need for the base case. If you're doing more base case calculations like this, what you're really doing is you're just kind of testing it out to understand what's going on in your own head. Okay? And so now what do we know? So now let's look at, so we assume that for any Bn, so let's induct on n, which means that for any Bn, the number of, the number of nodes at level k is n choose k. All right, so now we want a Bn plus 1. So we construct a Bn plus 1, right? And so this is how we construct the Bn plus 1. What we do, and now of course the thing about this is the problem that they all had on, everybody was complaining about last semester on the exam, was like, well, how do I construct a Bn plus 1? And so here's how you actually do it on paper, right? Here's how you actually do it on paper. You take off the B4 label of a B4, and you stick on a BN label. Okay? That's all. Now it's a BN. And you're like, what? Wait, you can't do that. It's not the right number of nodes, blah, blah, blah. Like, who cares, right? The point is not that this is not actually a BN. This is a B4. But pretend, right? There's no way you're actually going to draw out a full BN structure, right? Because you don't know what N is. So there's no way you're going to actually draw this out. So you just have to pretend it's a BN, right? So this is a B4. Pretend it's a BN, right? And so what do you know about a BN? So you know that at each level, the number of nodes is n choose k. And so what we're going to do here to construct our BN plus 1, we're going to take two of these and we're going to kind of mix it together like this, right? Like we do. Right? Now, you might say, but this is a B5, not a BN plus 1. You know, come on, this doesn't work, whatever. You know, no one was willing to just go with it. Or maybe some people were, but people didn't like it. Didn't like it. And I don't know why. Just, you know... I mean, here's the thing. If you were actually drawing this out on paper and you didn't have access to Inkscape, you could even do this with like a B2. Like, I don't care how many nodes you actually draw in. Like, I'm only doing this with this just because this is about the right number of nodes that'll actually fit on a screen, and it looks kind of like, if I say that this is a BN, you're like, well, there's a ton of nodes going on down there. I don't really know. I don't really care. So here's the way to think about it. Now we have to look at level K. Right? And so here's the thing to realize. At every level of a BN plus 1, you have, so at level K of a BN plus 1, you have what? Two things. You have level K of a BN, right? Which is, if we go down K levels, let's say we go down K levels, we'll find the kth level of a BN, right? And we'll find the K minus 1th level. That's the thing. We'll find the K minus 1 level of another BN, right? That's the trick. So this is the trick here to this proof. Okay? So at level BN plus 1, you have a level K, and you have a level K minus 1 of another BN. So what we're going to do here is write out a formula. That formula being this thing. And then I'm going to tell you a fact. Let's see, n plus 1 choose k, and then we're going to have n plus, oh no, I'm sorry, n choose k, not n plus 1 choose k. N choose k minus 1. So this is what we end up with, right? This is the number of nodes at that level. And so here's what we end up with is n choose k plus n choose k minus 1. And as it turns out, I'm sure all of you know exactly what this is, but let me argue. So there's actually an identity that gives us this exactly. And so let me tell you what that identity is. And you're going to, think, wait a second, isn't this cheating? And then I'll prove the identity. I'll prove it using buckets and analogies, okay? So here we are. So here's the formula, n plus 1 choose k. To which you say, at level k of a BN plus 1, you have n plus 1 choose k nodes. Perfect. Right? But then your question is, how did we get this equal sign here? Right? This identity right here. So how do we actually get this thing? And the answer is, I just told you it was true, and for about 10 seconds you believed me, right? So is it actually true, right? I'm just assuming the answer here. And so at this point, it's not a question of binomial trees. It's not a question of like doing all this other stuff. It's a question of combinatorics. It's a question of algebra, really. Now, you can do this with the factorials, and you can actually prove it with the factorials. And it's not completely useless to walk through it, so definitely you can prove using factorials, doing the algebra, etc. But you don't learn much from that proof. So here is the combinatorial proof of this fact, right? And so the combinatorial fact of this proof of this fact is basically, let's draw out a bunch of, here we go. Now let's space them. There we go. Okay, now pretend that this here, this is n objects. So don't count them. It's n of them there. So total, we have n plus 1 total, right? This is the n plus first object, right? Okay, so here's the proof. The proof basically goes like this. I'm going to color this one red. The rest of them are going to remain as they are. So if I go into a bag with n plus 1 things and I select k of them, right? How many ways can I do that? And so here's the answer to that. How many ways? Ways can I select? Can I select n plus 1 things out of a bag with n? I'm sorry. How many ways can I select k things out of a bag with n plus 1 total things? And the answer to that is, well, either we pick the red ball or we don't, right? And so if we pick the red ball, then how many objects do we have left to pick? And the answer to that is, well, we can only pick k of them, right? So if k is equal to 10, we can only pick 10 objects. If I pick the red ball, then and pretend that none of the rest of them are red, if I pick the red ball, then what I know is that I have to pick k minus 1 out of the remaining n. Sounds like n choose k minus 1. All right, cool. Now, what if I do pick the red ball? Oh, I'm sorry, what if I don't pick the red ball? Well, in that case, what I'm going to do is I'm going to say, okay, sounds like you're choosing, basically what you can do is you can say, okay, so go into the bag, take the red ball out, trash it, right? So it's not even in the bag anymore, right? If you know you're not going to pick the red ball, I'm going to go into the bag, I'm not going to pick the red ball. The other thing, you could say it in a bunch of different ways, like if I ever pick the red ball out, I'll just throw it back and keep choosing until I don't pick it, that kind of thing. So how many ways can we do this? So the answer is, well, then there's n things in the bag, still picking k, right? Because picking the red ball out of the bag wasn't done at random. We literally looked into the bag. This was a separate part. We took it out of the bag and we threw it into the trash. So this sounds like n choose k. And so the answer here is we add them, right? N choose k plus n choose k minus 1. And then the answer to that is, oh, that's the definition of n plus 1 choose k. All right. So this is like what they call this is a combinatorial proof. All right. So it's a cool little proof. You might not feel like it's as rigorous as a formal algebraic proof, but I think the point about these proofs is that the cool thing about these combinatorial proofs is that they don't like, yes, you can verify them with the algebra, but really the issue with them is that it's, in a sense, it's better for your understanding, because I promise you, if you unwind all the factorials and you do all the algebra, you will learn nothing from that. You will not learn anything from it. Like, you will get better at manipulating factorials, you'll get better at doing that algebra. But in terms of actually learning about how to deal with combinatorial questions, you won't learn anything. So in a way, like, this is a less precise proof that you learn something from. Or you could do a more precise proof that is kind of what like a computer would do. But again, the computer's just matching symbols. It wouldn't really be learning until we develop, until one of us develops AI, and then it'll learn. Okay. So, cool. So what is fact 2? There are 2 to the n. Maybe I'll actually just render that. 2 to the n. There we go. Doesn't look too bad. There are 2 to the n nodes in a Bn. And so actually this one can be done by induction as well. And so it's even easier induction, right? Right? Because I'm actually thinking maybe I should make this a test question. Nah, okay. It's okay. So if you look at a B0, has 1 node, and you know that 2 to the 0 is equal to 1. Cool. So then you assume, right, that a Bn, that specifically, Bn, right, some fixed, let's not even call it n, let's call it some Bt has 2 to the t nodes, right? And then what we do is we look at a Bt plus 1, which is 2 BTs combined together. It doesn't even really matter how they're combined together, they just don't lose nodes, right? We know that one of them becomes the left child of the other one and blah, blah, blah. But, you don't even have to, you should draw it, right? That's, in your exam proof, this is where you draw it again and you show that that's how you're constructing them. But on the other hand, we're almost done, right? Because 2 to the t plus 2 to the t is equal to 2 times 2 to the t, which is equal to 2 to the t plus 1, and now we're done. Right, so that little induction proof was mega simple. And so this actually proves that, and we know that the height of it is n, right? Or t plus 1 or whatever. So basically this is 99.9% of the argument about runtime, right? Because you know that if you're going to actually it's not exactly, yeah, it is. It's 99.9% of the argument about runtime. The other part of the argument is that basically you know that to find the minimum you have to search through all the head pointers, and if you're going to do that, the question is how many head pointers are there if you have n nodes, right? And let's say that the maximum thing you have is a Bm, then the question is basically how many, or how does m relate to n? And the answer is, at worst, Bm is the only, or I guess at worst there's a B0, B1, B2, all the way up to Bm, but you know that there can be no more than the log base 2 of n nodes in the Bm, right? So basically, the number of nodes in the Bm has to be less than this, right? Therefore, m has to be less than, m, not the number of nodes. The actual number of nodes just has to be less than n, therefore m has to be less than the log base 2 of n, right? And that is 100% because of this fact, right? If there's 2 to the n nodes in a Bn, then the height n thing has 2 to the n nodes in it, so there we go. So m has to be less than the log base 2 of n. So what that means is that we only have to look through a max of log base 2 of n things to find the min. And then what about merge, right? So for merge, it's the same business. Like if you have n nodes and we're merging with something that also has, let's say that n1 plus n2 nodes, then it's the same, right? Because basically the largest BM1 versus BM2 can be, right, is where M1 is log base 2 of N1, and BM2 where M2 is log base 2 of N2. Where I'm assuming that N1 is the number of nodes in the first binomial heap, and N2 is the number of nodes in the second one, right? So the point here is that the largest BM can be the log base 2 of N1, and be same thing with that. And then you know that basically this is binary addition, so you only ever do one operation per let's say k, where 0 is less than or equal to k, is less than or equal to, I guess, maybe probably max of m1, m2 plus 1, right? Something like that. And so, yep. And so given that, we know that the maximum of the m1 and m2 is about the log. So given that fact, right, given that the max of m1 and m2 is about log base 2 of n, I don't know why I'm writing it log base 2 all the time, let's just write LG. LG of n, then we know that all operations in a binomial heap take O log n time, right? And so basically here, this is merge, and merge can operate on two binomial heaps, or you remember that. Okay, let me say it more carefully. Merge is the operation, right, on a binomial heap. Basically, the only real operation. And so with it, you can do three things. And I mean, you can do more than this, but you can insert an element, right, which is basically merge our current heap with the new element, which is a singleton heap. 2, remove the max or min or whatever, which is merge our current heap minus the BK that contains the max with the children of that BK. And we'll go through that when we do the implementation. And then 3, we can merge two binomial heaps together, even if they, merge two, let's just say two different, right? But everything is really merge, right? You can either merge two heaps together, or you can remove the max and then merge, or you can insert an element. And inserting an element is the same thing as in a skew heap where you merge. So everything is always merge. Okay, cool. So, and all of these operations, all three of these operations are LG of n, log of n. Okay. So, okay, so I think that's basically all I want to do in terms of this. I think I'm done with the math. So, I'm not sure, let me promise you, we are not going to get through a full implementation of a binomial heap. We are definitely not going to get through a full implementation in 23 minutes. But let's see how far we can do. So here we need a binomial heap node, as usual, right? We gotta make our node. And so, as always, we're just gonna have int value. And the other thing we're gonna do is we're gonna have a vector of binomial heap pointers. And we'll call this children. All right. Maybe we'll make a constructor, new value, say equals 0, give it a default, and then we'll just do something like value, new value. There we go. Perfect. So that's all we need to do for that. Feels like we're making progress already, doesn't it? Okay. So notice what I had to do here, right? Normally, you're going to do something less crazy, like, for instance, I don't know, like a node pointer left and a node pointer right. In this case, we have to have a vector. Now, we can do this with dynamic arrays. I don't really... The only reason why I'm just not doing that is because that will require more work, and it's not work that's necessary for the binomial heap. It's just work that re-implements a vector, basically. So let's just keep this thing as a vector, like this. So now what are the things we do with a binomial heap? So we make a binomial heap with a constructor. We insert a new element. Right? We get max. We void that. And then what are the, maybe, let's make this public. All this public. Make a private. And then maybe a merge, right? Binomial, so merge with heap, and then we'll send it a binomial heap reference bin heap, right? And this, does it need to return anything? No, it doesn't need to return anything. But yeah, those are the three things that we need to do. Then, of course, the one thing we actually do need to do is, so we need a vector of, well, okay. Nah, you know what, let's just do it. So I'm going to cheat a little bit on the implementation. I'm just going to have a binomial heap node Superroot. Okay, so why am I calling this the Superroot? The reason why I'm calling this the Superroot is because it's going to be a node that will have a list of other BNs in it, right? But it's not going to be, it's not actually going to be a part of our heap. And I'll show you what I mean by that. Basically, I guess the way to explain it, and maybe you'll understand if I draw it like this, is like if I have a binomial heap. Let's see, where's a good binomial heap? So let's say that this, is our binomial heap right now, right? So let's just pretend that this is our binomial heap. And so what I'm going to do is I'm going to create a superroot. And I don't even care what the value is. And that's why I'm not even going to draw a value in here. But this is what I'm going to do. And you might think to yourself, well, this isn't part of the data structure. You can't do that. But the answer is I can do whatever I want, right? The point is that this is the superroot. It's imaginary. It's not really part of the data structure, but it's basically there for us to keep track of all these pointers, right? You could make a vector, but the thing is, I think if I make the vector, it's going to repeat some work twice, and I don't want to repeat that work twice, because then we'll have to keep track of all that vector calculus for our data structure, and then we'll also have to do basically everything else for the binomial node as well. So this actually makes it so that there's And if you notice here, like a B3, right? A B3 has like a B0, a B1, and a B2 as children. So that is another way to think of this, right? So if you look at this, this is a B0, B1, and B2 as children of a B3. So anyway, and so basically this is not a B anything, right? Because nothing, no Bn just has a B0, B1, B3, but no B2 or B4 or anything like that. Like if this were a B4, then there would have to be a B2 sitting here, but there's just not. Okay, so anyway, the superroot is imaginary. So some of its pointers can be null. None of the children's pointers can be null. Notice that this one doesn't have any pointers. This one has 1 and it's not null. This one has 3 and they're not null. But this B2 pointer is going to be null. So that's what I'm going to do with the superroot. Okay, cool. So let's open this up. Let's do this. Standard nonsense. Come on. There we go. So, all right. Okay, so the first thing we're going to do is we're going to say superroot is equal to new binomial heap node, and it really doesn't matter what the value is. So I'm not even, the value truly doesn't matter here, right? We're never actually going to look at its value. So we are wasting, it's a waste of 4 bytes. You might think, man, that's a huge waste, those 4 bytes. And then you remember how much a pointer takes in a 64-bit space, which is 8 bytes. So, I don't know, whatever, we'll fix this. Let's add them, let's say binomial heap, reload. There we go, that fixed it. And I forgot to do one thing. I was so busy creating the superroot that I forgot to, I'm not sure we're going to need to return anything, but if we do, then we will. So merge binomial heap node, and that's what we have to do. So okay, there we go. Not sure that that's, I'm not 100% sure, because as it turns out, I don't know if you know this, but I've coded one of these in my life, and I don't think it was live. So I'm just trying to think on my feet. So for insert, what we're gonna do, I think what we want to do for insert is we want to run merge on our superroot and the fake superroot that we're about to create. So fake superroot is going to be equal to a new binomial node, and then it's going to have a single child. And let's push back a new binomial heap node with the new value, like this. Okay, so what should happen in this case? Now in this case, we have a new node in the B0 position of this fake superroot. And so now we're just going to merge the two superroots together. And yeah, we'll just do that. I don't know if it's going to return the superroot or not. Yeah, let's just do that. And then here what we have to do is we have to clean up a little bit. I'll have to delete the fake superroot because we don't need it anymore. But other than that, I think we're good, right? I think so. We don't want to delete anything from... So we don't delete the child because the child gets stuck into the actual heap. So I think that's fine. All right. And so how do we get the max? We get the max by looking through... So we say... For, say, int I equals 0, I is less than, what? I is less than dot size I plus plus. And so, unfortunately, you kind of have to, I think you have to, I can't spell unsigned. There we go. So this is where the log n part comes in, right? We're scanning through all the children, and we're looking for the one that's the min. So current min index equals -1. Int. My typing is really terrible, mainly for, well, there's a lot of reasons for that. Okay, so if the p superroot dot children at I, right, so this is our bi dot value is less than, well, actually, let's assign it to 0. And then, of course, we're actually going to have to take care of the empty heap deletion thing. So current min index, right? Then current min index equals I. Okay, so now that we've found the min index, right? So what if the superroot children dot size, what if it's 0, right? Then we're going to throw a domain error, std main error, right, or something. I think if we include std except, and then we use like this. So I don't think we need the, what is it, the resolution operator anymore. The error is attempt to delete from an empty queue. Okay. Why is this not happy? The empty method should be used instead of size. Okay. If you insist, fair enough. Don't really care, right? That's not the point. You're missing the point. Yeah. Oh, right. And now we have to make this unsigned, which is fine. Okay. So now, what have we done at this point, right? We've checked to make sure that there's nothing or that there's at least a B0 or something inside of this, what should I call it? Heap. And we've also found the min index, which means we've looked through all the head pointers. So if we look at the visualization, right, you know how, well, let's just look at this again. So we're basically scanning through this, this, and this, and here we'll select this one, right? So we'll select this one, and we'll say this one's the min. Oh, there's one thing I didn't do here. So we have to check to make sure it's not just null. Because if it's null, then that's a problem. So, okay. Because remember that the superroot can actually have like a null B2. So that can be null. Okay. So we see here that, here we go. Current min index equals I. So now that we found the thing that we actually care about, what are we going to do? And the answer is we're going to remove the thing out of the so we're going to use p superroot. Let's do binomial heap node pointer p what should I call this? P remove root equals this dot children at the current min index, right? And then what we're going to do, we want to remember it, and then we want to remove it out of our list. So what we're going to do is say this one is equal to null pointer, right? And so then what we're going to do is we are going to, and so the reason why am I setting it to null pointer, right? The answer is because I'm taking the entire bi out. So I'm taking the entire b current min index out of the what am I out of the binomial heap. And then what I'm going to do is merge its children back in, right? So I'm going to merge its children back in. So how do we merge its children back in? So we'll do this. We'll just say merge p superroot. I like this construction, p superroot, and we're going to merge it with the what is it? The remove root, right? Because that's the thing. And then we have to do another annoying thing. We have to say int return value equals p remove root dot what value, and then we have to delete the p remove root, right? Because it's dynamically allocated, and then we have to return the return value, right? So this return value only had to survive for what, like one line of code here, but unfortunately we did have to do it just because that's what we had to do. Okay, so then the last thing we're going to do before we actually get to the meat and potatoes, the nuts and bolts, the whatever and whatevers, like the two things that, you know, the je ne sais quoi of this thing, right? We are going, so this is insert, this is get max, a little bit annoying. This one should be pretty easy. What we're going to do is merge p superroot with bin heap dot p superroot, right? And then we'll set that to our superroot. And then what we'll do is, I guess what we can do is we can go through the other guy's superroot and just tell him to forget everything, right? Is that what we can do? Let me think about that. Yeah, I guess we can do that. I'm just trying to think through this problem before I do something really stupid. Because we actually want to keep the superroot in the other binomial heap. We want to say for, or actually what we can do is even better than that. I think we can actually just, isn't there like a way to reset a vector dot, like, I don't know, you can set the, maybe erase, is there push back, is there like a clear, I think we can just resize 0. So basically what we're telling it to do is forget all of your children. Don't delete them. We'll take care of it. We also haven't made a destructor, but this would prevent the prevents double free when you're doing destructor stuff. Okay, so I think that's it, right? We just assign that and then we forget. I think that's honestly it. I don't think we have to do anything more than that. Okay. So we'll have to think about the destructor, which I didn't even make a destructor. So let's make a destructor. I'm not sure that we're actually going to implement the destructor today. We probably won't have enough time for that. I mean, we're definitely not going to have enough time to implement merge. So, you know. So I'm not really sure what we should do. Maybe we implement the destructor today, and then at the beginning of next class we implement the merge operation. Is this what I want to do? Yeah, I mean, I think in 3 minutes I can probably handle a destructor. I probably can't handle this merge algorithm, right? This merge algorithm is everything. Like, everything gets done in here. All of this stuff is really just helper code. So, yeah. I mean, you've all seen a recursive delete, right? On, say, the P Superroot, right? It's just going to go through, and so what is this function going to do, right? It's going to have a binomial heap node current. You can call it P current since it's a pointer. And then we can do something like this, and then we can do something like this. There we go. So what can we do now? So I guess what we do is we basically just say, like, if p current, right? And then we say for int I equals 0, I less than, well, we can even do it more simply than that. Auto heap node in p current children, like that. And so we can say rec delete, that's what I'm calling it, heap node. And then what we get to do at the end is we get to, I guess if p current, we'll delete p current, so we'll delete p current. And so here we'll recursive delete the superroot and then set the superroot equal to, wait, no. Well, it really doesn't matter, but some people like that. Okay, so we'll recursively delete on that, and then, so if heap node, oh no, we don't even need that. We'll just, yeah, if heap node, recursive delete on heap node. So that'll prevent it from calling on any of the null pointers. And I think that's it. That should really get us there, right? So that's our little recursive delete. Why don't you like it? Member function can be static. Who cares? No. We're not going to make this a static function just because it doesn't. No. Okay. And that's really it, right? Because I mean, so we've done a binomial heap delete. So here, I think what we're going to do in the end is return superroot A, probably. Either that or we'll make a new. No, we'll return superroot A. And obviously we're done now, right? So basically this is the thing that is going to accomplish our mission, right? It's going to basically go like, so it's going to go through so we'll have a carry pointer, and then what we're going to do is we're going to go through, let's say the max size is equal to p superroot A children dot size bigger than b dot size A what is it? question mark A colon B. Little ternary operation business. Just to shrink that down into a single line because we are uber lazy, right? So let's look at all of that. So if the one size is bigger, then we'll pick that one, otherwise pick the other one. And then what we'll do is we'll say for, actually maybe we want the min size. Let's reverse this. Because I want to just scan through all the ones that exist on both of them. And I don't know why I'm still working on this. Index equals 0, index less than min size, index plus plus. And then what we're going to do here is basically here's what we're going to do. We're going to say like if superroot A children at index and superroot B children careful at index, right? If they both exist, then we have to add them together, right? So then we'll add them together. So we'll create, and so once we add them together, we'll set them to p carry, which will go on to the next So it's going to index, right? So we'll set them to the next one so that it'll go up, and then basically what we're going to have to do is if we have a current carry, we'll have to remember it because then we'll have to probably deal with the current carry, maybe first or last, depending. We'll check if they both exist. If only one of them exists and there's a carry, like else if, right, superroot A children and p carry, right, else if superroot B children index and p carry, right. In this case, we add these together and make a bn plus 1, set it to carry. Same thing here, it's just we have to do it with A and B separately. If there's only one of the things, right, so if else if, say, p carry, right, but there's nothing else, then what we do is we say superroot A children at index is going to be equal to the p carry, set p carry equal to null pointer, right? So I think that's basically covering most of the cases. I'll have to go through and think to myself if this is all the cases. Of course, I'm 5 minutes over at this point. So, but the point is, this is basically the start of how it's going to go, and then what you have to do afterwards, and this is why we're definitely not going to finish today, is we have to go and, you know, what if there's a last carry? What if there's more in one than the other? What I mean by that is, like, what if there's a B0, B1, B2 in one of them, but then in the other one, there's like a B0, B3, B5, B17, B19, right? So if that's the case, then the answer is that, you know, we're going to do a little bit of merging down here, but we also have to recopy the rest of the data structure. So we'll have to recopy the rest of the data structure from superroot B into the superroot A, and so that's the point here. So we're going to so there's a bunch of extra stuff that has to be done. None of it is exceptionally complicated, but it all has to be done. It's just a lot of, you know, it's like, how do you add two numbers? Well, how do you add 10,284,300,007 to 52? And the answer is a lot of copying numbers down, right? Because you're not going to have to carry all the way up. And so, okay, so that's it for today. I guess we didn't get on to Fibonacci heaps. We'll do Fibonacci. We'll finish this implementation. I think we're uber mega close on this implementation. And then we will finish the. We'll do Fibonacci heaps next time, and yeah. When's the homework due? I guess I'll make it due next Tuesday. Today's Tuesday, right? Yeah, today's Tuesday. Due next Tuesday. It's 4 problems, so it shouldn't be too bad. Okay, so yeah, this is basically it. Merge is going to be huge, but what else are you going to do? And then we'll add our standard print functions, and then we'll, you know, watch this thing kind of come to life. I'm really uncertain if this thing is just going to explode or not, because I remember the first time I implemented it, I think it took me probably 2 hours to implement, and I definitely caused a number of explosions. You know, just because this thing is, as it turns out, it's finicky. I promise you it's finicky. So it's not, you know, it's something that you're going to be like, oh yeah, I've totally got it at 100%, and then it just blows up. Anyway, okay. So if it blows up, then who cares? All right, so we'll finish the implementation next time, and all right, that's it.